Log on, tune in, find out. Another good idea from Cambridge.
All aspects of split plot experiments.
Thank you. Good morning. The original title of my talk was Split Plot Experiments with Factor-Dependent Whole Plot Sizes. But yesterday evening I decided to make an entirely different talk, and to reflect that different talk I changed the title in Split Plot Experiments with Factor-Dependent Whole Plot Sizes, and this is the talk I wanted to present to you now. On the title slide there are two affiliations. The University of Antwerpen is also in the information booklet of this conference. I'm also an employee of TNO, that's a Dutch contract research organization in Holland, and that's relevant for this present presentation because the motivating example I'm going to present to you originated from a research project carried out at TNO. The research has already been reported in a journal article. It was published in the Journal of Quality Technology early this year, and it was authored by three authors: myself, Brad Jones of SAS, and Peter Goos, whom you know all about him by now. Here's an overview. I start with a gentle introduction to split plot designs. It's not entirely needed after the introduction Peter gave, but nevertheless I will go through that introduction again. Then I show how to construct the optimal split plot designs by looking more closely into the algorithm to make these designs. I will explain to you why this algorithm did not help for a project carried out at TNO about the production of coffee cream. So we needed a modified algorithm, and we made a modified algorithm. We studied several design alternatives, and at the end of the talk there's coffee, and there are also, prior to coffee, some recommendations. A simple split plot design. Suppose you have 4 whole plots with 4 subplots per whole plot. Here they are. Suppose we have one whole plot factor at 2 levels only. These whole plot factors are typically hard to change factors. They are hard to change in the agricultural settings originally, and also in the industrial settings I'm going to discuss. So here is the whole plot factor, and it is at 2 levels, coded with a -1 and a +1, and there are 2 whole plots with a +1 and 2 whole plots with a -1. And then already apparent from the initial whole plots depicted here are 2 subplot factors. These are easy to change, and these are also 2-level factors. So what we have here is in fact 2 replicates of a complete factorial in 3 2-level factors. What are we going to do with the results of such an experiment? Well, a common interest is in making a statistical model of the results, and the model includes an intercept. I forgot to mention that on the slide. It contains 3 main effects for each of the 3 factors, and also 3 two-factor interactions. So you will observe that there is no 3-factor interaction present, although you can estimate this 3-factor interaction. This is usual in industrial applications. For these applications we often ignore or assume that they are absent. We ignore 3-factor interactions and higher order interactions. This is about the systematic variation. We want to construct a model reflecting the effect of these factors. Now about the random variation, as Peter also has shown you, there are 2 variance components, there's a variance component between the whole plots, supposedly caused by the fact that it is very hard to change the hard-to-change factors in a completely reproducible way. And there is also a variance component within the whole plots or between the subplots of a whole plot. So the variance-covariance matrix of the observations, sigma, is block diagonal, at least if you order the results whole plot by whole plot. So a special feature of these split plot designs is the form of the information matrix for the model coefficients. It's x prime sigma inverse x. And this is in contrast to the usual completely randomized layout where the sigma inverse disappears or is a scalar, can be replaced by a scalar. The x obviously is treatment dependent. It depends on what treatment you allocate to the various observations. And the sigma is layout dependent. It depends on the whole plots and the subplots of the experiments. This is the simple introduction to split plot designs, and I'm now going to expose you to a slightly more complicated example, and this in the context of a coffee cream project. There is a large dairy company in the Netherlands called Friesland Campina, and these people are very proud of one among many of their products, namely their coffee cream. The coffee cream of Friesland Campina has a quite large viscosity, so if you whirl the flask around, it goes slowly instead of like water. And once upon a time, well, it's not that long ago, a few years ago, they decided to redesign the production process of the coffee cream. And the way they wanted to do it is they wanted to run an experiment with 9 factors and then make a model of the results, viscosity as a function of these 9 factors, and then look how you can conveniently employ these experimental factors to make a good new production process. Now, there were 2 hard-to-change factors, namely the number of process loops the coffee cream has to go through, 1 times or 2 times, and also the speed. About the first factor, this factor has to do with the piping of the production system. The one time a loop is just 1 series of loops and pipes, and the 2 times loop needs a disruption of the piping in the insertion of extra length of pipes and then restart of the process. So this is really hard to change, and the people don't want to do that very often. The speed factor is also a hard to change factor, and we will look more closely into that factor later on. Apart from these 2 hard to change factors, there were also 7 easy to change factors. There were 5 factors for which the people were interested in a quadratic effect, so they were included at 3 levels, or they were to be included at 3 levels. And for 2 of these easy to change factors, the people were interested only in just linear effects. So the model the people wanted to obtain contains an intercept, 9 linear terms because there are 9 factors, 5 quadratic terms because there are 5 3-level factors, and also 36 product terms. So these are simplified interactions. Full interactions take more degrees of freedom, but for a response surface, we think that just the product terms will be enough. So if you add all those numbers, you arrive at the number of 51, and at least 51 observations are needed to make this model. And it makes sense to obtain observations in excess of these 51 observations, of course. Now there was also a budget, and this budget was that we had room for only 6 weeks of experimentation. And these 6 weeks coincide with the whole plots, because at the beginning of the week people can do everything about the whole device to make this coffee cream, and then it had to be in action for a whole week. Also, it was possible to conduct 3 weeks with 7 whole plots, 7 subplots, sorry, and 3 weeks of 14 subplots. So in 3 weeks there were 7 batches of coffee cream to be made, and in 3 other weeks there were 14 batches of coffee cream to be made. So there was sufficient budget for a total of 63 observations, and this is well in excess of the 51 observations that were minimally required. Now, with all these requirements, a few 3-level factors, a few 2-level factors, 6 weeks, 7 subplots per whole plot, and also 14 subplots per whole plot, it's completely impossible to make a nice, balanced design based on some orthogonal array, much as I regret that. So we have to make use of an algorithm, and the particular algorithm we used maximizes the determinant of the information matrix X prime sigma inverse X. That's a quite usual criterion. It's called the D criterion, and we want to have designs with large values of this determinant. Now, the component X depends on the design. So if you have a design, you can evaluate the determinant. No, you cannot do that, because you have to make an assumption of how sigma looks. So we have to make assumptions about this variance-covariance matrix, but these assumptions do not enter the story for this morning. It's sufficient to say that the results you obtain with this algorithm are not very sensitive to the exact assumptions you make about this matrix. Let's look at the steps of a typical algorithm to maximize this determinant. The first step is very simple. Generate at random a design with settings of the whole plot factors and the subplot factors. And then the second step is try to improve this design by making changes of the settings of the factors. And that's what I'm going to demonstrate now. In this little scheme, there are 2 columns for the hard-to-change factors. There are also 2 whole plots there. The first whole plot has settings -1 for the whole plot factors, the hard-to-change factors, and the other whole plot has settings +1 and -1. Now, the algorithm proceeds as soon as this random design is generated by finding improvements to the determinant of the information matrix. So it tries to evaluate what happens if you change that -1 to a +1. If the criterion improves, it keeps the improvement, and then it moves to the next whole plot factor and to try a change there. And then it goes on to the subplot factors, and for this case it's a 3-level subplot factor. It evaluates what happens if you change that 0 into a +1 or a -1. So step by step this criterion is improved, and well, the algorithm cycles around over all the runs for several times until no improvement is possible, and there you arrive at your final design given this given this initial configuration. It could be sensitive to the start design, so it's usual to start several times afresh and then to keep the best design. And there a problem arises in this particular application. The problem is that the factor speed is completely linked to the whole plot size. The slow runs give rise to 7 subplots, because if you work slowly you cannot make many batches of coffee cream. If you change that to a high speed, then all of a sudden you have 7 additional subplots. So the fast whole plots are sized 14. And you have 7 extra subplots in addition to the existing subplots. And the problem then is that the settings of these suddenly appearing subplots are not known, so you cannot evaluate the information matrix, and you cannot evaluate whether an improvement has taken place. So clearly this algorithm doesn't fit with this particular application, and so we had to find a new algorithm or a modified algorithm. And the solution we found was quite simple. We switch off the exchange part for the whole plot factors. So we start with a fixed whole plot design, then generate at random the settings of the subplot factors, and then try improving these settings only. But to have a complete picture, you must consider all possible whole plot designs. Fortunately, in this quite simple example with 6 whole plots only, it's easy to enumerate all these designs, especially if you fix the total run size on 63. These are the 2 different designs you can make. Both the designs have 3 slow whole plots and 3 fast whole plots. 3 times 7 plus 3 times 14 makes the 63 runs which we have fixed in advance. They differ because of the replication for the factor process loop. The first design has proportional replication. There is a 2-to-1 ratio for the slow runs over the factor loop, and there's a 2-to-1 ratio over the fast runs over the factor loop. And the second design doesn't have this proportional replication. There is a 2-to-1 ratio for the slow speed, but a 1-to-2 ratio for the fast speed. And of course, if you relabel the factor loop, you have in principle the same design. Now, given these 2 designs, we can run a modified algorithm. The first design has a determinant of the information matrix of 2.202, or I should say a determinant raised to the power 1 divided by the number of parameters. This is a usual representation of these criterion. It makes nice, neat little figures instead of those big scientific notation figures. So the result is 2.202 for the first design and 2.193 for the second one. Now, the first design has a whole plot component, a whole plot design, which is orthogonal for the main effects for the whole plot factors. That is not the case with the second. So we expected in advance that there would be a difference between the criteria obtained here, but we were surprised that it was not, the difference is not very big. So to look into that more closely, we decided to make some design alternatives, and one of the alternatives is a set of 70 run designs. The first one has 2 slow runs and 4 fast runs. That's the only option if you want to obtain a 70 run design. And also proportional replication, a 1-to-1 ratio for the slow runs and a 1-to-1 ratio or a 2-to-2 ratio for the fast runs. The second design doesn't have proportional replication. There's a 1-to-1 ratio for the slow runs and a 3-to-1 ratio for the fast runs. And now the difference between the determinant of the information matrices is much more pronounced, from 2.448 for the first design to 2.364 for the second design. And now for the explanation about the difference in these 63 run and 70 run alternatives. We return to the 63 run designs. If we look at the contrasts you can estimate in the whole plot stratum, you have 3 contrasts: a speed contrast, 3 runs with a high speed, 3 runs with low speed, a loop contrast. For the first design, 4 runs with the setting 1 time and 2 runs with the setting 2 time. And you have also an interaction contrast, and this contrast calculates the difference between the 2 diagonals in the scheme. And there are 3 runs on each of the 2 diagonals here. So the ratios for the contrasts are 3-to-3, 4-to-2, and 3-to-3. And for the second design, this ratio changes to, well, it keeps the 3-to-3 for the speed. That cannot be different here. Now we have 3 runs for both settings of the factor loop, but now the diagonal elements here are for 4-to-2. So the difference is that the 4-to-2 originally at the factor loop now moves to the interaction. These ratios are important for the precision you can estimate the effects with. The best thing to do, what minimizes the variance of a contrast, is an equal replication on both sides of the balance. And now the unfavorable setting of the factor loop moves to an unfavorable setting for the interaction contrast. So in fact there is one unfavorable proportion, and it only moves to another effect here. And it is different for the 70 run effects. There we have a necessarily unfavorable proportion for the factor speed. You have 4 fast whole plots and 2 slow whole plots. But we have, for the first design, a nice proportion for the factor loop, 3-to-3 or 1-to-1 if you like, and also for the interaction, also 3-to-3. But in moving to the second alternative, both favorable proportions change into unfavorable ones. So from this intuitive reasoning, you can understand that the difference in this information matrix here is more pronounced than for the 63 run alternative. I move to some recommendations I can make. Suppose you have to do with factor-dependent whole plot sizes. Now, probably the best thing to do is to start with a fixed orthogonal whole plot design. Then you apply an exchange algorithm to find optimal settings of the subplot factors, and then you arrive at an initial design, which is at that moment not randomized. The next step then is to randomize the order in which you run the whole plots, and separately the order in which you run the subplots of each of the whole plots. I realized that this recommendation could be problematic if there are more whole plots. This is really a little bit tiny example, 6 whole plots only, and it's easy to enumerate all the cases. If you move to, well, 16 whole plots, it will be different, and it would be interesting to develop more appropriate methods for these cases. I forgot to mention that the article I referred to, the JQT article, is just a case study. So it could really be extended to something more thorough. And now is the moment to arrive at the last slide. Last slide is very simple. Thank you for your attention.
Questions or comments for Eric and Rosemary?
I thought it was very helpful the way you showed those ratios 3 to 3, 4 to 2 and so on. But in fact, the whole plots with the fast speed, shouldn't you have doubled all those numbers?
Let's move to this.
Yes, so for example, shouldn't the speed really be in the ratio 3 to 6 because you had twice as many subplots when the speed was fast?
I put this 3 to 3 ratio because I suppose that the whole plot error operates primarily on those 3 whole plots. So if you look only at the whole plots, there is indeed a 3 to 3 ratio.
Oh, I see. But surely there'll be a contribution from the subplot
Yes,
error.
I agree. There will indeed be a contribution.
Okay,
Sure,
so
sure, that's true. Because you average about over 14 or 7.
Yeah.
True.
So in that example, you said that the 4 to 2 ratio simply moves from the main effect to the interaction.
Right.
Is it not also true that that would affect interactions of loop with subplot factors?
Yes.
So you might think the
True.
second one would be better,
True.
although it's cancelled out with the orthogonality.
Yeah, this is more favorable because you move the unfavorable thing to an interaction. And you don't suppose that this interaction interacts with subplot main effects. Yeah. And indeed there is some improvement in the criterion.
There's a comment, I think, from both speakers. With these small designs, an aspect that you're not considering, but I think may be equally important, is the number of denominator degrees of freedom that you'd have when you do your mixed model analysis through REML, and then come to assess the effects. I mean, it's nice to have small variances, but if you've got very few degrees of freedom in your approximate f-test, then you're not going to get very far. And I think the pattern of confounding that you come up with, if I can think in the traditional sense, if you've got an ordinary split plot and you start confounding factors and you start losing your degrees of freedom at the bottom level if they're not completely confounded in one of the places. So I just wonder if you've looked at that in the context of the designs that you came up with.
Well, one approach that could be taken here is a Bayesian approach for the analysis. I completely agree that for 6 whole plots you have 2 main effects in interaction, a variance component, and to make matter worse, there are subplot effects also partly in the whole plot stratum. So it's a mess. And what you can really say something about is the subplot effects. And the whole plot effects, you can say something about them by doing something Bayesian, I guess. But
If you confound things completely, you preserve your residual degrees of freedom in the subplot stratum, I think is part of the point I'm making. So you need to consider that at the same time that you're optimizing the determinant, whether you're losing degrees of freedom that you actually need to have.
right.
Any further questions, comments? If not, so let's thank both speakers again.